Alright, today we're starting chapter 4, section 1, exponential functions. Okay. Now, good news, what we just got done with in chapter 3 is, I'm not even going to say probably, is the most difficult thing that we're going to do in this class. So if you made it through chapter 3, you're good to go. Okay, from here on out, it will be things that you have seen before. Okay, I say that because you probably have never been introduced to the method of factoring that we saw in chapter 3, where we're able to factor polynomials that are greater than degree 2, right? Getting the factors of the constant over the factors of the leading coefficient, doing synthetic division, like just mindlessly crazy stuff, right? Obviously, as I did the examples, I was covering 3 or 4 pages as I was doing them. Well, we're going to go back to things that we're a lot more familiar with now, and today is going to be exponential functions. Okay, so in this chapter we study a new class of functions called exponential functions. For example, if we have f of x is equal to 2 raised to the x power, that would be an exponential function with a base of 2. So as an exponential function, because we see that it's raised to an exponent, okay, but that exponent is the variable, okay. We have seen problems like this before. X cubed, is equal, or not equal, maybe x cubed plus 4, right? We've seen things like that. While we do have an exponent, right, the unknown is simply this variable here. When we talk about exponential functions, the unknown is going to be the exponent itself. Okay, and then it reads with a base of 2. Well, you think about a base, right? You think about a pyramid, right? The base is the bottom, right? The big part. Well, that's what we consider the base in exponential functions. So notice how quickly the values of this function increase. As a matter of fact, you could say it increases exponentially, right? 2 cubed is 8. 2 to the 10th is 1,024, and 2 to the 30th power is in the billions. Okay, compare this with a function g of x equal to x squared, where g of 30 is simply, where when we replace the unknown, which would be the base, which would be 30, 30 squared is just 900. Okay, so the point is that when the variable is in the exponent, even a small change in the variable can cause a dramatic change in the value of a function. And like none of them said it raises exponentially, but okay, that's fine. Today is also going to be one of those days where I appear lazy because I'm just going to do a lot of snipping. But we have seen that I am not shy from doing all the arithmetic, so I don't have anything to prove, right? So, to study exponential functions, we must first define what we mean by the exponential expression a of x, when x is any real number. Okay, in section P4, so again, P's, the P chapters are the prerequisite chapters, and I requested early on that if you didn't understand something, go through the prerequisite chapters. Okay, so if you need to be, have a quick reminder, quick refresher on exponential, well, the behaviors of exponents, go back and check out P4. Also, if you want to, I'm actually going over exponents right now in my Algebra Essentials course. So whenever I post a link to today's current lecture, I also always I post a link to your class's playlist, but I also post a link to all the playlists. Okay, so if you need more substance on exponents, then check out my Algebra Essentials playlist. And again, it's very similar to how I structure you guys, right? I do the chapter, I do the section number, and then I put what's in the chapter. So today, when I upload today's lecture, it's going to be exponential functions, right? So if you want to look at Algebra Essentials, it'll just be like exponents, exponent rules or something like that. So check that out if you need more help. And so P4, check out P4 if you need help. Or if you just like my voice a lot, which I know all of you do, then go check out the YouTube videos. Okay, so let's get back here. So in section P4, we defined a raised to the x power for all a greater than 0, and x is a rational number, but we've not yet defined irrational powers. So what is meant by 5 raised to the square root of 3, or 2 raised to the pi. To define a raised to the x power when x is irrational, we approximate x by rational numbers. For example, since the square root of 3 is approximately 1.73, is an irrational number, we successively approximate a raised to the square root of 3 by the following rational powers. And then that's the approximations, right? We know approximations. Intuitively, we can see that these rational powers of a are getting closer and closer to the square root of 3. It can be shown by using advanced mathematics that there is exactly one number that these powers approach. We define a raised to the square root of 3 to be this number. Okay, so, guys, I don't really know what we're trying to get at here, but I think it's along the lines of an exact number, which, if I recall, example 1 is what really hits at home. So let's just hit to that. All right, I mean, we all know about approximation, right? So let's probably gonna put this on the current page. All right, it fits. All right. Oh, that's what probably we're getting at. It can be proved that the laws of exponents, and this is very bottom line, are still true when the exponents are real numbers. Maybe that's the point they're trying to drive home here. Okay, so we're going to snip this, and we're going to put example 1 as well, because example 1, if I recall, we're just using a calculator here. Okay, maybe we'll do a new page for that. Okay, so exponential functions. The exponential function with base a, again a being the base, the big number at the bottom, is defined for all real numbers x by f of x is equal to a raised to the x power, where a is greater than 0 and a is not equal to 1. Okay, so we have to define that because, well, let's just assume what happens when a is equal to 1, right? When a is equal to 1, well, 1 raised to any power is always 1, right? And we're talking strictly about numbers that are greater than 0. So, and that's kind of what it just says down there. Yeah, we're good. Okay, so next up, we're going to evaluate this. And again, I think today is just going to be one of those snip days where I just snip and talk. So let f of x is equal to 3 raised to the x power and evaluate the following. Okay, so we're going to evaluate f of 5, f of negative 2/3, f of pi, and f of the square root of 2. So we've evaluated functions at different values before, and this is no different, right? So f of 5 here, f of 5 is simply just going to be 3 raised to the 5th power, okay? And 3 raised to the 5th power, we see down here, would be 243. Now, it gives you a nice, realistically, this is actually pretty good as for calculator keystrokes. Because I feel like this might cover 98% of the calculators that you do use. So you'd hit your 3, little caret there, and a 5, right? B, f of negative 2/3. So again, same thing. What we're going to do is we're going to put, and we'll just go and erase this. Oh, I didn't realize I changed the color. Well, that's good. Okay, so we do f of let's not change color. We'll do red. I think red is easier to see on this white, huh? So f of negative 2/3. What we would do is we would take the 3 and raise it to the negative. Ooh, my arm is touching. Sorry. Negative 2/3 power. There we go. Okay, and in doing so, we would get approximately 0.4807. Okay, and of course, we can see how we do that for the rest of them. All we're doing here is just evaluating and using a calculator. All right. I know, shame on me for not being able to do this in my head, right? That's what I hate, right? I'm good at math, but people just think I'm a human calculator, and I'm not. Math is more than arithmetic, and I really hate it that many students don't get to enjoy the actual beauty of mathematics. They have to do mindless computation like this. That might be a conversation for Wednesday. Who knows? Okay, so graphing exponential functions. Let's see what all this fits. Okay, so we're gonna try to get this to fit. Oh, I also don't know if I said this or not, but guys, we have 1 month of classes left, and that's not including our Thanksgiving break. Is that crazy? All right, so example 2, or actually starting at the top, graphs of exponential functions. We first graph exponential functions by plotting points. We will see that the graphs of such functions have easily recognizable shape. Okay, so first of all, we will be graphing exponential functions by plotting points, but similar to what we did in the last chapter, we're going to see what it looks like when we plot the points, but then after that, this is going to become a new parent function for us, right? All the parent functions we talked about before, well, we're adding another one today. Okay, so example 3, draw the graph of each function. So a, f of x equal to 3 raised to the x power, which would be this one. So this is our input, our x values, and this would be our output, our y values, right? So we plug in negative 3, we get 1 over 27, negative 2, we get 1 over 9, so on and so forth, okay? And as we plot those points, we end up with this red line here. Okay. Next, we're going to have g of x equal to 1/3 raised to the x power, and again, same thing. This is our if we plugged in the negative 3, negative 2, all that. This is our input. If we plug it into this function, again, this is b, and then this is our output. Okay, and then we notice that it creates this blue line. So no, we're not going to talk about that yet. About the behavior of it. Okay, so all we did there was just simply plot the points. Figure 2. Oh, there we go. Okay, yeah, there we go. Yes, so we're gonna snip this as well as figure 2. Okay, so what we're doing here is we're going to get an understanding of what these parent functions look like and how they behave with varying, I guess it looks like bases. Yeah, with varying bases here. Oh no. So we have to make that smaller. It's kind of good. Alright, I'll move that toolbar down at the bottom. Obviously on the YouTube video you won't be able to see it. Maybe I can just make this smaller. We'll do that. There. Okay, so what else do I need to snip here? Oh, I already did that. Okay, good. Alright, here we go. So, this reads, supposed to be a laser. This reads, figure 2 shows the graphs of the family of exponential functions f of x equal to 8 to the x power for various values of base a. All these graphs pass through the point 0, 1. Okay, so that's interesting. They all pass through this point. Because they all pass through 0, 1 because a to the 0th power is 1, right? You can see from figure 2 that there are two kinds of exponential functions. If we have a between 0 and 1, then the exponential function decreases rapidly. If a is greater than 1, then the function increases rapidly. So notice all of these. We have 10, 5, 3, 2, right? Then we notice that we do indeed increase rapidly here, okay? Whereas if we have a fraction, well, it looks like we decrease rapidly, okay? We can kind of skip over the note. The note will be there, but I don't feel like I need to read it. And we're good there. Okay, so now let's get to the actual graphs. Okay, so the exponential function f of x equal to a raised to the x power for a greater than 0 and a not equal to 1. All right, so this is the important stuff for today right now. It has a domain of R. Okay, R, again, if you write it like that, you just kind of do two vertical lines and make an R. Okay, it means all real numbers, right? And all real numbers is basically negative infinity to infinity. Okay, so our exponential function has domain of R. That means it uses all available x's. Okay, but it only has a range from 0 to infinity, and we can see that, right? It looks like we have a horizontal asymptote here on both of them, and when we shoot up in both as well, right? So it looks like we have the domain of R in a range of 0 to infinity. The line y is equal to 0, which I just said, right, is the asymptote, and then we see the following shapes, right? So when we have a whole number, or not necessarily a whole number, sorry, a number greater than 1, we see we shoot up. If we have a fraction, we see that we go down. Okay. This is the introduction to that parent function we were just talking about. Okay. Furthermore, if you recall on the other parent functions, I said, hey guys, so we're going to have a landmark. Okay, remember talking about a landmark, and for all the ones we did in chapter 3, that landmark, that little point that we moved around, was at the origin, right? If we need to move up 3, left 3, whatever, we took it from the origin and moved it around. Well, for exponential functions, we're going to take it from this point here. There we go. From 0, 1. So like if we need to shift up 2 units, we'll go 1, 2. Okay? Or down 2 units, 1, 2. Or left, right, things like that. This is our landmark that we're going to be moving around. Unlike the other ones, which were at 0, 0. Alrighty, so this particular problem, it says find the exponential function f of x equal to a raised to x power whose graph is given. I guess this is one I could have probably done the arithmetic on, but so we know that a graph or an exponential function has the definition of an exponential function is this, right? F of x equal to some base raised to the x power. Okay. Well, A is showing us. Oh, I shouldn't have done yellow there. A is showing us that f of 2 is equal to 25. Okay, so 2 is taking the x place and 25 is taking the y place. So I can essentially, again, let's think of this as y is equal to a to the x, right? Because f of x and y, they're essentially interchangeable. Okay, well, then 25 is equal to a squared. Okay, again, the 25 is taking the value of the y, which you see here, and the 2 is taking the value of the x there. Okay, well, what squared will give me 25, and that would be 5. So a would be equal to 5, and so that means we can come back up here and say that this exponential function is 5 raised to the x power. Okay, and of course you see that because I snipped the solution already. You're welcome. Okay. And let's talk about B. B is very similar. Okay, so B would be again we'll just go ahead and write y is equal to a to the x. A to the x. We're going to start there. Okay, and we see down here that the x is a 3 and the y is a 1/8. So we can say 1/8 is equal to a cubed. Okay, well, what cubed will give me 1/8? And of course we see the answer. There would be 1/2, right? So a would be equal to 1/2. Okay, and that makes sense, right? Because if we take 1/2 and we cube it, right? Well, 1 cubed is 1, and then 2 cubed is 8. Okay, so that's how we identify graphs of exponential functions. We need to know the actual value of the graph at a point. Okay, and in this particular case, again, we got that point there. We got that point there. We have to know the value of the graph at some point in order to actually figure out what the function is. Okay, now we get to the good stuff. Right, so again, similar to, um, as a matter of fact, I said chapter 3 was going to be our hardest one that we come across, and and it's true, because everything we're going to be doing now is just basically what we did in chapter 3, right? So all the transformation rules that we did in chapter 3, we're going to do the exact same. We're going to follow those rules here in chapter 4. Okay, so it says use the graph of f of x equal to 2 raised to x power to sketch. Maybe I want to kind of show that this is not part of that. There we go. To sketch the graph of each function, states the domain, range, and asymptote. Okay, so if we were to look at this and you know, for a moment, you know, try not to put your eyeballs over here. All right, let's actually look at g of x, or let's look at a real quick. So it is g of x is equal to 1 plus 2 raised to the x power. Okay, so if you recall, if we are adding or subtracting to the parent function, okay, if we're adding or subtracting to the parent function, and of course we can kind of think of this as g of x is equal to the parent function, which is 2 raised to the x power, and then the plus 1. Okay, so that would tell us that, okay, so we're going to take this parent function, and since we are adding 1 to the parent function, we're going to shift that parent function up 1 unit. Okay, and of course that's what we see over here. Okay, so we see that the blue line is my parent function here, and all we're doing is shifting it up 1 unit. Again, the same rules that we saw in chapter 3. Okay, and as I mentioned, we take our landmark here at 0, 1, and we're going to shift it up 1 unit. And that's that. Okay. B. Let's see. I'm gonna keep that A there. I'm not gonna erase it. But B. Okay. So B. Again, same rule that we saw. Well, I don't have to do anything here. Same rule that we saw in chapter 3, right? Well, we are taking the negative of the parent function. Okay. So if we're taking the negative of the parent function, then we're gonna reflect it across the x-axis, right? Now, real quickly, let's do this. All right, if negative 2 raised to the x power is the negative of the parent function, which it is, all right, well, then 2 raised to the negative x power would be the negative of the variable, okay, just to kind of show you the difference between those two, all right, and of course, the negative of the variable would flip it across the y-axis, right, so it would look something like this, okay, but since we are taking the negative of the parent function, we simply mirror it across the x-axis, and that's where we get this graph right there. Okay. All right, next up, and lastly, rather, I don't need, let's see, okay, and the last one we have here, C, notice we are subtracting from the parent function, okay, again, the parent function is 2 raised to the x power, and we're subtracting 1 from it, okay, and again, the same properties that we saw with the transformation in chapter 3 we do here. If we are subtracting from the variable, then we will be adding, or then we'll be going to the right 1 unit. And of course we can see that. We can see that in this graph right here. Notice how we take. It's not that apparent, but let's try to make it apparent. Let's see. All right, so I'm gonna make this mark here at 0, 1 right here. Okay, hopefully you're seeing it. Okay, and we shifted it to the right 1 unit. No, sorry, that's not 0, 1. Sorry about that. This is 0, 1. Okay, we're gonna take that because that is the parent function of blue line, and we're gonna shift it to the right 1 unit. Okay, and then we can make our exponent. We can draw our exponential function through that point. Okay, so again, exact same rules that we saw in chapter 3. We obey those rules here in chapter 4. Okay, and one moment. Alright, I'm back. And next up. I don't like that. That's just showing more behavior. I don't think it's that important. Okay. Next up, we'll talk about compound interests. Okay, so those of you that have taken statistics, oh no. Okay, so it did this to me. Oh, shoot. Okay, so it did this to me the other day. And I had to actually close out. Let's see if I can. Okay, let's try. Let's see if we can reset it a little bit, see what happens. Oh yeah, the pen's not working good. Alright, so let's see. I'll give it one more try, but like I said, today was just gonna be a snip day anyway, so it's not the worst thing. If today wasn't a snip day, then I'd have to restart everything. Instead, what we're gonna do is we're just gonna read off of this. Actually, I do wanna, for notes, let me give this one last good college try. Well, that's a shame. As soon as I get up, my pen just stopped. Yep. Okay. Yeah, we're just gonna read. That's unfortunate for the notes, but we have the YouTube video, right? So, all right. So right here, exponential functions occur in calculating compound interest. If an amount money P, called the principal, is invested at an interest rate I per time period, then after one time period, the interest is P times I, and the amount A of money is da da da. Right? Let's see. Honestly, I don't think we really care about that. This is what we care about: compound interest. Okay, so looking at this compound interest formula, we're going to see that we've got 1, 2, 3, 4, and 5 t right here, the little t there. We have 5 variables. Okay. Now, in order to solve equations with an x amount of variables, you need to know x minus 1 amount of variables. Okay. So for instance, an example of that would be everything that we've done to this point. We've usually run with 2 variables, right? An x and a y, right? And we are usually given one of those to find the other. Well, compound interest, there's 5 variables, right? But you're going to be given 4 of those 5 in order to find that unknown, okay? All right, well, A of t is the amount after t here. So A of t, is again, it's essentially our y, right? It's our output, right? And it's the amount the amount of money we'll have after t amount of years, given our principal rate and things like that. P being principal being the kind of like the initial amount. Okay, R is interest rate per year, and when we talk about interest rate per year, when we talk about any sort of interest rate, when we say 2%, we're not saying we're not putting 2. Okay, we're putting 0.02, which would be 0%. N would be the number of times interest is compounded per year, and T would be the number of years. Okay, that's pretty easy. Okay, so a sum of $1,000 is invested. So $1,000 would be my principal. That's what I'm initially putting in, and we see down here that it is indeed in the P position, the P spot, right? P being the number in front of the parentheses. Just so you know, it's pretty weird for me too, sitting here scrolling and doing this. So yeah, I'm sorry, it sucks. At an interest rate of 12% per year. Okay, now 12%, we're not going to be putting 12, right? 12% in decimal form is 0.12. And of course, you see that in all of these as well. Find the amounts in the account after 3 years of interest, compounded annually, semi-annually, quarterly, monthly, and daily. Okay, so the only other one that's in all 5 of these would be the 3, which is going to be find the amount in the account after 3 years. Okay, 3 years, well, that's going to be time, right? 3 years isn't any of these other ones, and so you'll pretty much kind of know essentially what number goes where by just the language that is given to you. Okay, and then it says compounded annually, semi-annually, quarterly, monthly, and daily. Okay, so the compound number of times compounded would be n, and so that n is our denominator here, and is what we multiply the time by in our exponent. Okay, so if we are compounding annually here, okay, oh, that's interesting. So we're compounding annually here, then that's just one time of year. So we're going to put a 1 down here in this denominator and 1 up here, and then we just do the arithmetic here. Okay, this is just the arithmetic. And remember to do PEMDAS, okay? PEMDAS before or as you go about doing this. And if it's semi-annually, then that's twice a year, so we have to put the 2 there. Quarterly, well, there's 4 quarters in a year, so we put the 4 there. Monthly, there are 12 months in a year, so we put the 12 there. And daily, there are 365 days in a year, so we put a 365 there. Okay, and as we do that, notice how the numbers are all pretty close to the same, right? We have 1404 to 1418 to 1425, 1430, 1433. But notice how the more that we compound, the more money we actually get, right? So if we just compound it one time, well, we only get $404, right? Because we initially invested 1,000, right? But if we compounded it twice, we get a little bit more. We compound it 4 times, we get a little bit more. 12 times, a little bit more. But if we compound it every single day, we get a little bit more than monthly, right? But of course, this is with the principle of $1,000. The more money you have, the higher you actually get, the more you compound. Okay, but this is just how you compound or calculate compound interest. Again, we just look at our formula here, and again, we have our 5 unknowns. All you do is plug in whatever's told to you. That's literally it. Okay. And then lastly, for today's section, example 7, calculate the annual percentage yield. One moment, this really bothers me that that didn't work out today. So like, yeah, for some reason it's well no. See, it's skipping everywhere, and that's why I can't snip correctly. But we'll try one more. Yeah. All right. Yes, I could use my finger, but it's a lot less precise. But I could do that. Snip it to the notes. Anyways, so example 7. Find the annual percentage yield for an investment that earns interest at a rate of 6% per year, compounded daily. So we'll be using our formula up there, right? After 1 year, a principal P will grow to the amount, right? So we don't have a principal number yet. We just want to know how much that principal would grow. Okay, at 6% per year. We're looking for the annual percentage yield. So if we're growing at 6% per year, the annual percentage yield, if we plug in all this, would be 1.06183. Okay, and again, that's just P times that. Okay, we are not given any sort of principal. All we're trying to figure out is the annual percentage yield, which would be everything in the parentheses, which would be everything beside the P, right? And again, that would be 1.06183, which is 6%. Okay, and of course, the formula for simple interest, and this formula, guys, this formula here, is again, I don't teach statistics, but in my humble and non-statistic person mind, is the most important formula you're going to have, right? Because this is a formula I use quite often in my finances, right? So we have A is equal to P times 1 plus R, okay? 1 plus the rate. Let's see. Yeah, that's about it, okay? And 1 plus the rate. If my rate is 6%, then we would have 1 plus 0.06183, which is simply the same thing as what we saw in our long formula there. I feel like I know I hand waved through the interest and stuff, but if you have any questions, obviously you can email me. I have that sign up sheet. I didn't really want to restart this program here, or restart my computer, because then it chops up my recording, and then I have to take care of that. So that does conclude today's lecture.